I think it's time to get started. Hello everyone, I'm Gautam. I'm from Cybersecurity Cluster of DSC SASTRA, and with me, Hariharan will be assisting the session. Today we are going to see about buffer overflow. Buffer overflow is like really an old bug, which is one of the first bugs which are common in the DOS systems, from DOS systems to Unix till today. Even in the Windows 10, we have buffer overflows. So why would you learn this? Like why would you even learn anything? You are learning with maths and in academics. Why would you do that? Like you have to learn that so that you'll understand the upcoming concepts, right? But buffer overflow is a really cool bug. If you learn this, you could explore a lot of things. Like you might learn for finding 0 days. 0 days is like bugs that vendors doesn't know it existed are called 0 days. For example, if you find a buffer overflow bug today in Windows 10, you found a 0 day, and 0 day, or if you find a 0 day, they'll pay you really good money. There are a lot of people out there in the world. They make a living of finding only 0 days. There is an initiative called 0 Day Initiative, where people come together and work together to find 0 days, and they make really good money. Because let's say Windows is most used operating system in the world. Like billions of computers use it. What happens if like really bad person finds a 0 day and hacks it? So like billions of people get affected. So it has a really good value in doing, but it is not easy. A lot of people are looking for it, and Windows 10, any operating system, has been in the wild for a while, so it is going to be really tough to find 0 days nowadays. So another reason to learn this type of bugs, not just buffer overflow, like really intensive bugs, memory intensive bugs, or certifications like OSP, like offensive security certifications, everything you will need to learn stuff like this. And my favorite thing is to hack games. Like a lot of games has come through this. It will have at least one buffer overflow even today, but it will be tough to find. Like you could reverse the integer. For example, if your money in your in game cash is like 1,000, and you could like subtract it, and you could make it to go underflow, which means you could turn that 0, and if you subtract it, it will go underflow, and you'll get insane amount of money. You'll go in negative, and after negative, you'll go the highest number in integer. So you can do something like that. Some of the games that have been hacked are Shadowbane, Final Fantasy. So what do you expect in this workshop? We'll be discussing about buffer, stack. Stack plays an important role because there are two things we'll be discussing: stack and heap. But in this workshop, we'll be exploiting only stack. So you could call this a stack overflow also. So we'll be learning how to exploit the buffer overflow, from what is memory to like executing your own code, getting your reverse shell and stuff. And there will be live demo. Live demo is going to be like literally like 80% of the workshop. So a buffer is just a like temporary space to store the data which is being processed. Let's say if you're like mining Bitcoin, you can't like save every data in the CPU, right? You have to, for calculations you can do in CPU, but for saving the data you can use caches. The the caches which are near to CPU. If it is not enough, you have to use the RAM, stuff like that. So buffer is just a space where you store data when it is getting processed. So before understanding buffer overflow, you have to get to know some stuff. It will be like a revision class for your OS course. But if you are not from CSC, or if you are from first year or second year, no problem. It is a simple thing. When you execute a C program, what happens? That's what you're going to see now. So this is your memory, virtual memory. So that from down we have the low address till the high address. This is how it looks. This is what happens really. So the text here is your code, and it has only read-only permissions. So this is your code, and your initialize data, initialize the variables, and uninitialized variables. And above that, you have heap. Heap is really big. So like most of the space is occupied by heap, and above that we have stack. So you can see here the heap expands from down to up, and stack grows from up to down. And above that you have global variables, which is also called as kernel space. Here is where all the environmental variables will be stored, and the stack will contains all the local variables, and the heap will contains all the that, that when you allocate dynamic memory, and your global variables and initialized and uninitialized will be stored in DSS. Initialized will be stored just below that, and below that you'll have your code, your C code which you just type. So you have to understand what stack is. You might have learned stack in data structures also. That is very same to that. It is just an implementation of that. So what happens in stack is like when you call a function, a stack is like stacking the plates one on another. So if you want to remove the first like you could say here like last in first out. Last plate which you place on the top, you can remove that one first. So the stack is a very simple thing. When you like it stores all the data needed for a function call. For example, if you are calling int main, your stock will store all the data that is required for int main. It will store all the parameter values. It will also store the local variables data, and it will store your return pointer. Return pointer is like after completing the execution of the function, you have to return to the main thread, right? That is also stored in stack. We'll see about that later. And the main thing you have to understand is that it stores parameters of the functions, local variables, and return address. So you can learn. I know you might not understand all about stack here because stack, heap, all these things are you could that is a 1 week worth of topic. You can't learn it in 10 minutes or 20 minutes. But if you're interested in it, you can just Google and Wikipedia. There are pretty good resources. Heap is similar to that, but here the data will persist in the stack after execution of the function. Your data will get clear, but in heap, you're allocating space dynamically, and the data will persist even after the function, even after the return routine. But if you want to clear data in heap, you'll use free or delete later. Malloc, you might have heard of malloc in C, right? So that is the implementation of heap. There is a system called used in the kernel to do these things. So we'll understand what we'll understand what stack is. Stack contains of 4 things: a extended stack pointer, a buffer space, extended base pointer, extended instruction pointer. We'll understand one by one what are those. Extended stack pointer holds the address of top stack. So ESP here, it stores the address of the top stack. I'll show you how it looks when the real execution of the program is afterwards. Yeah, I'm sorry for that. A buffer space is which it holds all the data which is required for the calculations or things. This is the data we are going to control, so you have to remove that. Extended base pointer contains the base of the stack. This is used for calculating the indexing of the stack. For example, so this is your stack looks like. So you have your EBP here, like base pointer, and you will have your local variable stored under the EBP, and you will have your argument stored above it. And RET, which you see here, is the return address, which you will be using in the exploitation of buffers. This plays the important role. You have to remember that. And have an extended instruction pointer. This will contain the address of the next instruction. For example, if the function execution is over, the compiler should know where should it go and execute the next thing. That is stored in EIP. So now we understand EIP and things. I'll show you a demo in Linux. Can you see the screen? Virtual logs, can you see? Is it visible?
Yes, Gautam, it's visible.
Yeah, cool. So I'll show you a simple demo, like how it looks, how the memory layout looks like. You can see there is nothing here. So I'll create a file. I'll create this .c. So we'll create a simple C program. And for now, we'll just return it, return 0. So I think okay, we'll save this. Save that. So now you can see this is my simple C program. It does nothing. It just opens the function in main and it will return it. It will just get out. So nothing much happening here. So we'll execute using the DCC. DCC is a compiler used in Linux. Linux systems is all available for Windows. You could data search it. I haven't used this in Windows though. We'll name it memory layout. I'm just compiling the test.c file and I'm saving the output in a file called memory layout. So what I'm going to do is I'm going to show you what is the size and the registers, like in the stack, what is happening there. So you could see here. So the text, the code which we typed is 131.358. Data which the program uses is 528, and BSS number BSS used here. Yeah, it's big. I think, yeah, it has uninitialized values. I think, yeah, here. Yeah, uninitialized data. We have the BSS there. So now you could see that we don't have any uninitialized variables. Now let us simply uninitialize. We'll just simply introduce a variable which is not initialized. I'll do that with. So now you could see I'm just simply wrote a variable without initializing it. So now we'll execute this again. You see the size again. Okay. I think. I don't know where it's working. Okay. What it should happen is that the BSS value should change. I don't know why it's happening. Yeah, okay, let's continue. So now we understood what the stack looks like. So what you have to remember is that it contains function arguments and the return instruction EAP which we saw, and EBP, it doesn't really matter, and it also contains the local variables. Now what we are going to do in this workshop is that we are going to give the buffer a data whose size is greater than the buffer size. So let's say that the buffer can hold only 8 bytes, but we are giving here 10 bytes. If we give 10 bytes instead of 8 bytes, the 2 extra bytes will flow to the next register. So let's say we are giving argument 1, we gave 10 bytes instead of 8 bytes. The remaining data will flow to return EAP. EAP contains the next instruction pointer, which means we might override the address of next instruction. So if the next instruction is some like 4 to some values, and if we override that, we'll get a segmentation fault. You might have seen in C or C++ programming, you always get a segmentation fault, which means the memory address which you should not you are accessing memory address which you should not supposed to access. So what we are going to do in this workshop is that we will change the EIP. So you saw that if we give a data which size is greater than a buffer size, it will just overflow and overwrite the next register. Here next register is return register, which is EIP. So if we craft a payload which will override the EIP, and if it will make the EIP value a specific value. For example, we are controlling a address like 4 to something we are controlling, and we are overriding the buffer. We are overflowing the buffer and overwriting the EIP register. We could craft a payload which will set the EIP value as address which we control. So now after the execution of the program, after the execution of the function inside stack, the next instruction which it will go is to the code which we control. With that, we can execute our own code. For example, if we want to get a reverse shell, we could put the starting of the reverse shell code in the EIP, and after the function call is done. The function is inside the program. That is a valid program that is verified by the administrator or user of the victim machine. Victim did that program. We are just exploiting the bug in it. After overriding the EIP, it will get redirect. The executor will get redirected to our malicious code, and we'll execute our malicious code. So now we'll see how it is done. Hariharan will take over from here. Thank you.
Thank you, Gautam. Now I'll be showing the practical demonstration. By the way, I'm Hariharan from the cybersecurity cluster as well. As Gautam already explained about the buffer overflow, now we will be actually doing a practical demonstration on it. Is my screen visible, Gautam?
Yeah.
Okay, cool. I'll get to the point. I have my Windows machine running on a VM. It's always recommended to use your Windows on your VM because you're gonna do something with your buffer overflow and it might really crash your program. So it's better to do it on a VM. You can do it on your normal Windows too, but then need to take care of it. And before starting anything, you need to switch off your Windows Defender. You can go to the settings and you can switch off your Windows Defender. That's because it's gonna interfere in your buffer overflow process. So it's gonna tell that it's a virus or something. It's gonna stop it. So you need to switch it off. And then from here, we can start our demonstration. First, we need to know the IP address of your Windows machine. So for that, I can use something called netdiscover. I'm just going to type sudo. And this is going to give me all the IP address which are connected to the interface VLAN 0. It will take some time. Okay, so we got the IP address. Usually for VirtualBox, you'll have a thing like this. So this is your Windows IP now. I'm just stopping this process now, and I'm. So after I get my IP address, so what can I do next? I need to connect to my one server, which is okay. So before doing this buffer overflow, we'll be using a exploitable server called one server. It's an exe file which is running, and then you'll also be using something called Immunity Debugger. The link will be posted in the chat. It's also easy to get it. It's a GitHub repo. You can put one server in your browser. You can get it, and you can also put you can also download Immunity Debugger. So now the thing is, for starting this exe, you need to start it as an admin always, and even your Immunity Debugger. you always had to start it with admin access. Okay, that's done. Now we start our immunity debugger also with our similar fashion. We need to start with an admin access. Okay, so from here, the thing is you need to attach your one server here. You need to know how what registers, as Gautam explained about the registers and stuff. So you need to see that what's happening when you're exploiting this machine, right? So you can go here and you'll have an option called attach. There you can see one server, you can attach it. And there we go, we attach our one server now, and then it is all ready to go. But then before doing anything, you need to start running this one server. So now this is these both are dependent on each other. If you close your immunity debugger, you can see your one server also getting closed. So it's both dependent now. So if you run it from here, basically your one server is also running. Now we can use something called netcat, and you can man netcat if you want, or if you have any doubts about netcat. But then the command which we will be using here is netcat nb. So n is for it's only number this one IP address and without any DNS, and then V is for verbose. So we get a verbose for the server, so you can see all the details in it. And then we are going to connect it to the IP address which we got for the Windows. And then, okay, so one server always runs on port 9999 by default. So I'm giving that. And you can see that I've connected to my one server, which is on my Windows machine. And then for more details, I can put something like this. And then you can see this is your verbose. So you can see all this if you put a verbose command. And then now you can see that you have some stuff right here. So you don't know what it is right now, but then we will be learning each and everything which is over here. So these are all some vulnerable. So this machine, this vuln server is made to exploit for buffer overflow. So you can see different type of buffer overflows here, but then the one which we will be seeing today is stats, and then we'll be seeing something called trun. So trun is beginner friendly. You can do it easily. Now the next step is to see which is vulnerable. So that's called spiking. The first step for buffer overflow is called spiking. So you see that if a machine is vulnerable or not, I mean, to check what's vulnerable and what's not vulnerable. And then we start making a script here, okay? So the script looks something like this. And then I'm naming it, I'll be naming it something like a spike folder. So I'll be naming it as stats.spike. Naming one for some reasons, okay? So, and I write my script for spiking. So this is for checking if my stats is gonna be vulnerable or not, or you can do a buffer overflow in it. So we do something like this. So you're reading the lines from the you're just having a read line. Then okay, and then this is a format for doing spiking. You need to have an S before and an underscore before you start, right? So now we check strings like where you have stats. Okay, and then you give a space in it, and then you send some random characters to it. So as Gautam explained, you'll have something like, you're going to overwrite your EIP and EBP also. So after from your buffer space, you come out. So you need to overwrite your EBP, and then you need to overwrite your EIP. So we are going to send some random characters and see what's happening into the server, or is it having a crash or something. So if you have a buffer overflow, usually it crashes. Your immunity debugger is going to tell, yeah, I had a crash. So now you can see that I'm running the program here. It's coming. Okay, I can increase the font by a little. Yeah, this is the maximum I can do now. The thing is, if I save this and I run this SPK spiking folder, you can see that there are stuffs running around here, but then you'll see something interesting in a way. So saving this. And then I'm just running the this one, okay? So for that, I need a tool called generic send TCP, which is usually installed in your Kali Linux, and Pareto is by default. If not, you can you can download it using some GitHub repos, which is available in the browser. it's generic. Then you have a send, and then it's TCP. So you just click and it's going to give you how the format is, how to input. So you have some generic send TCP, you'll have the IP address of your Windows, and then your one server is running on 9999, and then you have something.spk. So we had made some stats SPK, and then this is your initial and final bound values, which we don't require for this particular stats. Okay, so TCP, and then I'm having my IP address here. Okay, and then I'm having, oops, I'm sorry. And then it has some something like this, and then I'm gonna use stats 1.spk, and then I'm gonna give a value like this. So you can see it's going to connect to your Windows machine, and then it's gonna do something to your world server. We'll see what's happening. You can see your threads are running here. We'll leave it for about 5 to 10 seconds. Usually, pen testers do this. But the thing is, I'm going to give you a spoiler right now. Stats is not vulnerable. It is completely good. So you don't have any problem with your stats. So I'm giving a spoiler right now. But then if you're doing a buffer overflow attack, it is always recommended to leave it for more time. You can see that still the threads are running here. Yeah, now it stopped. Okay, cool. Now the thing is, stats is really good. So what we can do is we can do something called the next we can take is trun. So trun is going to be vulnerable. We know that. I'm giving you a spoiler again. Trun is beginner friendly. It's really good. The thing is, I need to start my scripting again for trun. So what I do is I do okay. And then I do the same thing here, read my line. And then I have my trun and with a space. And then I'm going to do the same thing, string. Oh, oops. And then I'm going to give 0. And I'm just going to save the file and do the same thing with a generic TCP, but then I'm just running my trun SPK spiking file. So now before that, the thing is usually with Immunity Debugger, there's a small issues when I used it. The thing is, it doesn't work as when you do some spiking. The thing is, it's already overwritten and stuffs are already happened. So the thing is, it's always better to close the thing. Run it again. I know this is a tedious job to do, but then you need to run it every time you do some work. So there are some shortcuts for it, restart the whole thing, but then this is a better way to do it. It's more easier to do this. I'm attaching right now, so you can see again it has started. I'm running the program, so you can see the running statement here. So I'm doing this again. And you can see that it has paused on its own without doing anything. So I'm stopping this. You can see that it paused on its own and it's going to give an access violation when executing. So I'll make it more bigger for you to see this. So you can see your access violation when executing. The thing is, I sent a random characters into the buffer. The thing is, when I sent this in stats, the only thing which happened is it did not overwrite your EIP or an EBP. So it was completely normal for that. But the thing is, for trun, the thing was, it was a buffer overflow. It can be vulnerable to buffer overflow. So thing is, it started writing its, you can see this right now. You have your ESP. Started writing everything. You can see a bunch of A's which is put here. Then it has come here. So the EBP has some 414141. So these are hex characters for A. So you can see 4141 over here. So it has overwritten your EBP. And it has also overwritten your EIP. So you can see that here. It is 41414141. So that's basically the hex for A. So you can clearly see that from spiking that your trun is vulnerable to buffer overflow. So we did this method to check if it's vulnerable or not. So it is. Proceeding to the next step is called fuzzing. So fuzzing again is a check for if it's a vulnerable, but then you send a bunch of A characters by writing the script. So I again start to write my script over here. The thing is, I have copied the script I've copied the script over here because it's gonna take a lot of time if I start scripting. I'll explain how my this one is working. Excuse me. I'll just. Okay, so my fuzzing script is right here. What I do is I open my this one, and then I'm making it's a py it's a Python file, so I'm naming it something like a py. So I name it fuzzing1.py, and then I'm having the script copied here. The thing is, it's connecting to a socket, which is our Windows IP, which we need to put it right now. The thing is, it's going to send a bunch of A's again. So you can see that the buffer is equal to A into 100. So it's going to send 100 in turns. So we'll see how it's happening. So if your loop is running, you will have your socket, which you need to input your Windows IP here again. Yeah, you can see that you have your Windows IP right now, and then you have your port at 9999. So, and again, you have your trun. The thing is, you need to put it in this way. So it has a specific way how you put it because that's how it's gonna run. So, and then you have your trun, and then you put your buffer. So basically what you do here is you send 100 characters, time by time, and then you can see that it's going to have 100, then 200, then 300, and you see exactly where it's starting to crash the program. So that way we can come to know an approximate amount of bytes at which EIP starts. As Gautam said, you need to find the address for, you need to find where the EIP starts so that we can send a reverse shell, or you can send some malicious code for doing a buffer overflow. So this is thing is, for starting a reverse shell, you need to know something, where you need to know where your EIP starts. So that's so basically fuzzing is for that. The thing is, you can see that I wrote my bytes crash that. So when I see this one here again, even the immunity debugger crashes, I'm just going to do a control C, which comes out of my program. It's going to tell me how much bytes it has crashed at. So that's how the program works. The thing is, before doing this, you need to make your script executable, your Python script as executable. So for that, you use cmod plus x, and then you have the thing. So I name my name as fuzzer1.py. This is not a problem here. Coming out, so I need to do the and then okay, I named it as fuzzing dot okay, so that's fine. This is an executable now. The thing is, again, I need to do this. I know it's going to be tedious while doing this. It's going to take some time, but then attaching it again. So you can see that your program is paused here. I need to run this. It's running successfully now. The thing is, I'll be doing my fuzzing, and you will see that when I run this program, you can see I'm just making it a bit more bigger. You can see that suddenly your immunity debugger will crash. It's gonna pause here automatically. And at that same time, when I see that, I'm just going to press Control C. This is only for finding approx. So if you do it a bit late or anything, it's fine because you're just going to find the approximate value. So executing my fuzzing 1.py. The thing is, if I do this, it's gonna run. You can see that it's running, but then you'll see suddenly it does take some time. So you can see that it is running. You can see it's still running, but then so you can see that it has been paused now. So I did it. The thing is, oops. Is there any problem with my scripting? I think there was a problem with my scripting. It's fine because, okay, cool. I'll do one thing. I have a fuzzer py already written. I'll just do that. Again, I need to close this thing. I'm sorry for if the code had some problem. Okay, running it again. I think I have something called fuzzer.py. Yeah, I've already written something called fuzzer.py. So it is a ready-made code which I already typed in. We'll try with this. Okay, so not a problem. We'll try with this. And it's already made an executable, so do not need, running it again. So I need to press Control C when it pauses. So it has paused. Now you can see that this script worked correctly. So my script had some problem last time. So you can see that fuzzing crashed at 2100 bytes. So now we got an approximate value at where it crashes. It's not the exact value, it's an approximate value where it crashed. If your guessing is as strong as mine, so you'll know that the next step is going to be finding the approximate value. I mean, you need to find the exact value with this approximate value, how much we got. So it's, before this, right? So you might have some 2000 bytes, or it might be 19, something like that. So you need to find the exact value. So that's the next step, which is called as finding the offset value. Okay. For finding the offset value, the next thing, again, we will be doing is writing a script. The thing is, over here, you can see that your it did cross that. You can see your stuff like that. It has overwritten it. So again, closing it, coming back at my admin access. Okay, cool. I've attached it. The thing is, finding the offset value, you need to do some stuff before starting it. So you need to, what we call it as create a pattern. So if I create a pattern, I'm exactly going to know where it is starting. So suppose if I create a pattern like 1, 2, 3, 4, 5. So it's if it's crashing at 5, I exactly know. I mean, if your EIP is getting overwritten at 5, so I exactly know it's 5 bytes. But then that will be that'll be a tedious job to do. But then, so we have something called Metasploit framework pattern create Ruby file, which creates a pattern for you. So I'll create that pattern, and we can see that we actually had it on 2100 bytes, right? So the file is in user share Metasploit framework. Then you have your tools, you will have it on your exploit, and then you'll have something called pattern create a Ruby file. Okay, it's gonna take some parameters, which is L, and then we are going to make exactly for 2100 bytes. Okay, so when we do this, it's going to take some time. Yeah, it popped out. So the thing is, I'm just going to copy this, and I'm going to put it in my script again, and I'm going to run. I'm just going to modify my previous script. I'm just naming it a different file, but then it's going to be the same script almost. Okay, you can see that I've already done this offset here, but then oh, it's going to take some time erasing this. I'm sorry. Okay, the thing is, the offset had exactly the same value, so it doesn't matter. Whatever I copied, it's going to be there in the same thing. It's going to take some time to, actually go there. So I need to do it. So basically, let's do one thing. So this is the same thing which I copied from the Metasploit right now. The thing is, when you do this, it's going to give an exact pattern at which your EIP crashes. Okay, so you will again use another tool to find how the pattern looks like, and you're going to find the exact bytes. So I'm closing this program. I'm just going to let me see if it's running my Windows when my Immunity debugger is running. So yeah, perfect. So now I'll be executing the offset script. Okay. The thing is, now you'll see that it has paused, but you can see that your random characters have gone through this making it a bit bigger. You can see that clearly now. You can see that it has gone through ESP. You can also see your pattern has come through this. It has gone through the EBP and it has gone through EIP. So you have this particular character, which is 38 60 6 F4337. I'm gonna do this, and I have the exact same file where I started, but then this will be like some pattern find kind of thing. So you'll have a pattern find here. If I'm wrong, it's okay. Yeah, you have your pattern offset, and then you have the same thing, which is L2100, and then you'll have your find command. So this will be something like Q, and whatever we had the pattern, right? So we had 3866F. You have 386F4. I'm sorry. The thing is the font is really small, so I can't. Yeah, when you do this, you can get the exact. So your the tool is going to give you the exact match at with the offset happen, which is 2003 bytes. So we found where our EIP starts. So your EIP starts at 2003 bytes. So we got the value for, the starting point for EIP. That means half our job is over. We can see what's now vulnerable, what thing doesn't have a protection memory, which will be the next step, or in the upcoming steps. And then you have this right now. So cool. So you have your 2003 bytes. We need to keep that in our mind. And then we can go for the next step, and which is now seeing how the thing works. Again, this is a checking method for 200 bytes. What you do here is it's very simple. You know that your EBP is getting overwritten. You know that your EAX and ESP is getting overwritten. The thing is 2003 bytes correct? That's the next step. You need to find if 2003 is correct. What I'm gonna do is the idea is send bunch of A characters, into A into 2003. So that's going to fill everything with A, and then I'm gonna do something like plus B into 4. Basically, what I'm doing is I'm just checking if my 2003 is correct, and I'm going to have my bunch of B characters having overwritten the EIP. So this way I can check if 2003 is correct. Now, for that, I written my script again. Okay, cool. Done with this. The thing is, again, I have written a script for this, and this will be let me see what's the okay. So not this. I'm sorry. So it is overwriting. So exactly. So this is a script which we use for your overwriting. So basically, that's the logic which I told you. You're seeing if 2003 is correct. And then what you do is you send up 4 B characters, which is going to be converted into hex, obviously. So it's going to be like 42, 42, 42, 42 in your EIP. And if this works correct, what we found what we found about the 2003 is also correct. So this is overwriting your EIP. So a check again. Again, I have this written in my not this again I'm sorry. Okay, so running this right now, and then let's see what's happening to our program really. Okay, running this program, and then let's see what's happening when we write this overwriting.py. You can see it got crashed obviously, but then let's see what's happening really in the registers. So you can see your stuff got replaced by A's, and then you come to your EBP, we have 4141 again. Over here it's A's. The thing is, when it comes to EIP, you'll have 42424242, basically the hex for B. So our 2003 is 2003 bytes is correct, and your EIP starts from there. And we checked it by sending 4 Bs, and which is also working. This brings us to the next step, which is finding the bad characters or something like that in our shellcode. So I'll explain while doing the code. The thing is, bad characters are something like if you have a unfortunately, giving a spoiler again, unfortunately in Tron there's no any bad characters, but then I'll just explain the basic idea behind the bad characters. The thing is, for a bad characters, the thing is, in the hex dump you might have some particular things written. In your EIP you might have certain commands written. Maybe it is like an add ABC according to assembly language, like that. The thing is, if you're having a bad character on exactly somewhere in your EIP, and when we run a shell code in future, which we'll be doing the last step, we run a ESP, a EIP, something in EIP, it's going to interfere with our existing shell code with the, for example, I gave an add command. So it's going to interfere with something like that. So these are bad characters. Something like already a pre-existing command which interferes with our own shell code, that's going to be bad for us, because your shell code doesn't even execute in the particular particular place. So that's going to really affect your shell code. Unfortunately, I can't show you bad characters right now because there's no any bad characters in Tron. The only thing which we'll be neglecting is the null byte. Usually we do that for every particular program. Again, running this. Cool. So now I'll be showing you the I'll be showing you the script for how bad character works. So I'm gonna send a bunch of characters here, which is obviously going to be starting from 1 to start up till FF. So these are all hex dumps. You can see the hex dumps when there's a particular problem. Now we send everything over here. The thing is, when you have a bad character, obviously these are going to be affected. So you can see that exactly I've done this plus B, and then I start with my bad characters. If I had some command in pre-existing command in my EIP, something like add A B C, or any command here, you can have anything here. So when I have that, obviously it's going to be affected. You can see that when you're sending this, suppose example, if I have my add command in my 5th or 6th position, and then I send my these particular bad characters there, you can see that your 5 plus 6 will be added actually, and then be sent it to some particular pointer address. This is where we find there's a bad character, and then your hex dump is going to give something like BO. So it's a B and O, and it's going to be the bad characters at per particular position. So if we have a bad character, there is an alternate step which is also present in one server. There is one of the this one like Tron. There is also something else which is vulnerable to this particular bad characters are present in that. But in Tron, unfortunately, you don't have a bad character, so it's easy for us to do our work. We can execute our shell code directly without any interference and stuff like that. So this is the code for the bad characters, and that's it with the bad characters part. So I can't show you the bad characters, unfortunately. So let's get out and see what's our next step. The next step is to finding the right module. So this is where things get tough and things get really interesting. Having my character, so basically finding the right module is going to take you some steps to do this. First thing, the prerequisites for having doing this thing is going to your browser in your Windows machine, and you need to download something called Mona modules. Again, Kadiravan will post the link. you can see a GitHub repository, and you need to download this particular mona.py. After downloading, you go to where your immunity debugger is located. For me, it's in program files x86. You can see something called immunity inc, and then you'll have an immunity debugger. And then you're going to see something called py commands. You need to post your mona.py here. Mine is here. You can see my mona.py is here. The thing is, this step is going to be a little bit hard because you need to now find which protection memory is good for exploitation. When I tell protection memory, I need to explain you something here. So you will be having some dependencies like DLL files which are running for your vuln server. For mine, you can see here. If I go back, sorry. If I go back to my folder, you can see that you have these particular files which are used for running the vuln server. And then you have something called essfunc.dll. So this is a DLL for this one for running for vuln server. Particularly when you have something like that, there might be a chance if it's vulnerable to buffer overflow. Obviously, it's not easy to find, as Gautam said. It's not. It'll be really hard to find. It's also an old vulnerability which is really hard to find. The thing is, if you have some DLL function, DLL running back, there might be a chance that your protection memory is not, your protection memory is false for everything, which I'm going to be showing you right now. For doing this, you'll have a small command bar here, and you're going to type something called mona modules. Okay. And this is going to show you what protection memory is bad and what protection memory is, true for this one. So I'll show you that in a minute. Yeah, you can see a mona module has run now. So you can see some particular stuff going on here. I wish I could make this a little bit big, but then doesn't give me that thing. So you can see this is your essfunc.dll. The thing is, there is many things, many protection called as rebase, safe, SEH, ASLR, NX compact, OSDLL. You can see all that stuffs in the top, and you can see something like false everywhere. And this is a place of attack for us because all the protection is false, which is really good for a hacker. And you can also see this, but then unfortunately, this is not related with anything with us. So yeah, if you're doing a buffer overflow, you need to check each and every pointer address for your work. But then again, giving a spoiler for run, this is essfunc.dll is going to be the one which we will be attacking, and then this is vulnerable. So I note the address, which is 62508000. The next step which I'm going to do is finding. Okay, the next step I'll explain again how this is going to come. The thing is, you have particular addresses, right? So if you have a program, and imagine if you're writing your program in your main, and then you have some function. So it's going to particularly jump somewhere. You're going to jump to that function when you call it, and then again return back to that with your return address. Okay, so this is something which is really important for us now. When we jump, what we could do is at that point of jump, we could put our ESO. We know that essfunc.dll is now really vulnerable. What we could do is we could bring this func.dll, the jump ESP for this, and we can do something like that. So we can insert our malicious code for the essfunc.dll. Again, I'll show you all that, but then this is how you find it. So this is the methodology for this particular step. You insert your essfunc.dll on that particular address, which we found right now. And then we are going to insert our malicious code inside that. Okay, so you need a dependency, which is your essfunc. So you're using essfunc.dll to insert your malicious code. Now, before that, you need to go to your Windows machine back. And then you need to find something called jump ESP's opcode. So jump ESP is what we require. Now, I told you, right? So if you have a jump, you could actually break that point of jump, and then you can insert your func.dll. So that's a very good way for finding which is, particularly a write module. So before that, I'll just show you the opcode for that. For this, you need to use the locate, and you need to put nasm shell. You can see the Ruby here. Just copying it out and pasting it. It does take some time to get the shell back to us. Yeah, you can see now. The command which we will be using here is jump esp, and we need to find the opcode for that, or the particular, yeah, so the opcode. So, and I do something like this, and there you go, you have something like ffE4. The thing is, we need to find where this JMP ESP is there in our immunity debugger. Again, you need to close it and attach it. But then before that, this is what you need to remember, ffE4. And converting this into hex, you'll have something like, you'll have like X, FF and something like that. I mean, not this, obviously, but then you have something like that for your hex. So yeah, so closing this thing, going back to our immunity debugger. Okay, you can see it much more clear now. So found the ffE4, that's what we need to remember for jump ESP. Again, I can use something like, you can use the Mona modules to find where the jump command is. It's literally impossible to search through here where your jump ESP here is. You'll have a lot of things going on here. So you can again find with the Mona modules. I do something like Mona, and then I find the particular this one. So I put find, then I'm running a parameter search like this, and then I'm having my /x ff x e4, right? So e4, yeah, and then finding my ess func.dll. So you know that the ess func.dll was suspicious because all this one was false, all the protection memory was false with it. So you can have the ess func.dll. Okay, so something like this. When I run this, you can see about 9 pointers coming here. There'll be about 9 pointers here, and you can still you can see that all the addresses has false over here. As a pen tester, you will be for finding the buffer overflow, you usually see all the pointers, search for all the pointers. Giving the fourth spoiler, the first one itself is vulnerable to, so that you can use the 625011AF. So using this, we can get to our EIP. So I'll be explaining that step later. But then what you need to remember is we got the pointers for the inside the DLL function. Through this, we are going to give a malicious code. So I told you, right? So ESS function, through ESS function, we give a malicious code. Now, remembering this value 625011AF, I'm going back to my code. Yeah, going back to my code. Yeah. Okay. I need to explain two things here. So already you can see the address has been noted here, 625011AF. You need to know about something called Little Endian architecture here. Little Endian, you have two Endian architecture. One is your big Endian and one is your little Endian. The thing is, in little Endian, the stuffs are reversed. So you'll start from your right and end in your left. So you'll have your 1, 2, 3 going from your right side to your left side. And in your big Endian, it will be something like, big Endian is a little bit complicated. The thing is, you'll be, breaking into many parts or something like that. But then what we concentrate here is your little Endian architecture. You'll have your, as I said, so you'll have your 1, 2, 3 starting from your reverse order from your right to left. So what I need to do is I got the address. So you can see that it has about 8 characters and hex has 2 characters each. What I do is, as I told, I'll be reversing it. So you can see that you have your AF first, then you'll have your 11, then you'll have your 50, and then you'll have your 62. Basically, what I did is I reversed this at the back. You can see your 50 coming after this. You can see your 11 coming after this. And then also you can see your AF coming after this. So it has basically reversed by 2 bytes. That is your little Indian architecture. What I basically do here is I get that particular address. So that particular address is what? So it is ESS func.dll's pointers which are being used. So that's it with this. So I can so you remember this, right? A into 2003 is for our getting into our EIP, and now I get to the IP address. So I'm just gonna you can see some exciting things right now. So okay, so you know what I'm gonna do? It does get a little bit confusing when you have such type of things. Okay. Am I running my Wallet server with an admin access? Not sure. 1 minute. Yeah. Got it now. Having it again here, I'm running the program. And things get really interesting here. You can see how your EIP is going to get overwritten with this ELL func, and then how we are going to get to the last step for finding our getting a reverse shell into the ESS func, using that particular pointer which we found, which is vulnerable. And then we are going to get the access to the whole Windows machine from my Kali machine. So this is what we're going to get in the climax. So, and then you can see that I'm running my write module .py. Things didn't get, I think I need to see how my write module is. 1 minute. My IP is right, so hoping this is also correct. Okay, so this is not something which I expected. Okay, so I made a small mistake. I forgot to do something. You had to set something. Remember, I was telling about the jump PSP. I had to set a breakpoint there, which I forgot. I'm sorry about that thing. So starting my thing right now. Got a bit confused with the script and stuff. Sorry, I'm sorry. Okay, I had to do something here, which I totally messed it up. I had to set a breakpoint, right? Remember, I was telling about the jump PSP where we need to find our jump PSP, and then we have our breakpoint over there. I had to find it. Okay, so I find it, and you can see that my address had FFE4, which is your jump PSP. And for getting a breakpoint here, you do something like an F2. And then you can see that this is highlighted now, and then you can you're having your breakpoint there now. Now I could run the program. So I have a breakpoint over there. Now if I run that, my EIP is going to be getting the ELL func.dll's address. So that's what I messed up in the last step. Getting it done again. Hopefully, yeah, I have to start running this. Hopefully this runs. There we go. We got it correct this time. You can see our the thing which we got. Remember the 62, 50, 11, and AF, which is your ESS func dot this particular address. So basically, What we did here was using the dependency of your ESS_func.dll, I am creating a breakpoint at my jump PSP so that I'm not allowing it to jump anywhere. I'm directly going into my EIP, and then I'm going to insert my malicious code with my ESS_func, which is your last step. This is your particular step where you got the, you got your ESS_func, overwriting your EIP. So as we are done with that, we can move on to the last step, which is your finding, getting a root access or whatever getting a full access of your computer. Somehow you reverse shell your Windows machine, and then you do that. So explaining this step again, because it was a bit confusing from the end. So this step is called finding the right module. Finding the right module basically is seeing where you have no protection memory, finding something which is not protected, like your ESS_func.dll was sus there. And then you can see that all was everything, about your SEH, safe SEH, and everything was false. So it's a point of attack for us. Then you use the, the particular address, and you find what is there, get all the pointers related with the ESS_func.dll, which we got about 9 pointers. And I gave you a spoiler that this was, vulnerable. The first one itself was, good to go. I do this, and then I find my pointer, then I go to my program back. So going here, what I do is I getting the address using a little Indian architecture. I get the whole stuff, and then I try to exploit this. Okay. The thing is, as a pen tester, what you need to do is, suppose if this was not, you could have taken the second pointer which we got, use the same thing, and run the same thing. So you need to do this. You need to continue this process. And before even this, we had some DLL over here. You might find a lot of DLL dependencies, in a program. So it's not like you'll have only one or two which is easy for you. Buffer overflow is tough to find. It does take a lot of time, as Gautam said. You need to check everything. So you know how frustrating it is to check everything, but then that's how buffer overflow works. And if you get it, you might even get a whole access to the computer. That's really cool. The climax is really cool, but then you need to work for it. As I said, Trun is beginner friendly. You will have everything in the starting itself, but then the rest of them, we had stats, we had Trun. So the rest of them is not like that. It's going to take you some time to do it, but then right now this is your right module. Now our last step is to get shellcode. The thing is, we will not be doing the shellcode. We will not be programming the shellcode. We will make MSF Venom do that. So MSF Venom again is a Metasploit's tool. Okay, MSF Venom is particularly used for creating payloads. You can get a reverse TCP. It's really it's famous for reverse TCPs. So I'm using something called MSF Venom, and then I'm going to get my Windows, and then I'm having my shell reverse TCP. Okay, so this is what we needed. So Windows shell reverse TCP. And then now we are going to give our L host. Okay, for that, I need to do one more thing. I need to get my, I need to get my Kali's IP address, which is my host machine right now. So you need to get back to that. So creating a reverse shell, you need to get your own IP address, which is this, okay. I got my L host. Okay, I'm putting it here. And then my L port can be something, anything like 4444. We will be listening to this port later, when we are exploiting the machine. So this, you need to remember this number, whatever you put here. So it's 4444. And then we use something called exit func is equal to thread. This is nothing but to make your whole thing stable, your whole shell stable while using it. Again, now we are going to put f. Again, you're using a param called f, which is your file type, and over here it's C. I'm using C to get my this one, which is C for the programming C. Okay, and then through that I might get my shell code, which is in hex form, and then I can use it in my Python file. The next one is your architecture, which is x86 here. That's cool to go. And then you'll have one bad character, which I already told you, which will be the null character. So we use this null byte character everywhere. Usually not used in our program. So putting that as well as here, so you can see that it's all good to go. Just making it sure it's okay to go. So I have my L port, my exit function, I have my file type, my architecture, and I have my character. Yes, tell me.
So if you are wondering why we are neglecting the null character, is that null character is used to indicate the end of the execution. So like even you can use it in your HTTP request also. As in, like if you specify null character, the request will be it will end there. Next request will start from after the null character. So if we exclude the null character, what will happen is that the code which we are supposed to execute might end somewhere in between, which is not supposed to end there. You can continue.
Yeah, so thanks Gautam for that. So null character is used for that. We don't have any other bad characters, fortunately here. So if you had some bad characters, you had to put your, remember I told about the bad characters which Run did not have any. If you have some other modules which has a bad character, you should include here, so that your shell code, which is coming right now, will modify itself for this particular bad character, and then we'll give you a shell code. So going for it, hopefully it works. It does take some time to get your shell, hex code. And there we go. Two things to note about this. So this is your shell code in a form of hex, your reverse shell for your which you'll be using in your program in a script. Two things to note here. You'll be using something called no operations in a while. The thing is, I need you to note this payload size, which is 351 bytes. You need to see how much this is. You need to note that as a pen tester. Usually for buffer overflows, we note the payload size. The thing is, this depends upon our script which you are going to write now. We are going to copy this. Already my script is ready, so I don't need to this one. The thing is, I need to copy this. We are writing a Python script, so we don't need a semicolon. We can directly copy it from here, and then we can insert in our Python script. Okay, so clearing this. I need to see what my file name was. So yeah, it's overwrite.py. So you can see that my overwrite.py has already got the shell code which we used. This is the same thing exactly what we got in our MSF Venom. But what I did was I just inserted an overflow, and then I put my shell code here, and then inserted in my shell code. But then before that, you might be wondering, what is this? We had this in our previous code for getting the ESS func.dll's the pointer which was pointing towards that thing. And then we have something called no operations right now. So what are no operations is basically we will not be having anything going through there. So suppose if you have something like for example, I'm just using the space. Suppose you have something, you had your ESS func.dll starting from here, and then you start. I hope this is visible to you, whatever I'm doing here. So yeah, the thing is, you might start your shell code from here. So this will be your shell code. Things might get really interfere if something was there in between this. So what we do is we give some no operations, 32 bytes. You can see we have given exact 32 bytes of no operations, so that we don't we don't interfere with anything. We are happily good to go here, because Trun does not have any memory restrictions or something. Usually in examinations like OSCP, they try to give you some payloads, the size of the whole thing, the whole memory size. That time you'll have a problem with this, because you're lavishly giving some 32 bytes here, but then you might want to reduce if you're having an examination where the payload size has been given. Remember, payload size was 351 bytes. We have no problem, but then again, the 351 bytes. So what if the OSCP exam gives something like 200 bytes or 250 bytes for your whole stuff? So you need to break your code and see how to use it within that. And then we can't lavishly spend 32 bytes there. We might put 8, or you might put 4 or something like that. But then we have no problem of having such a memory memory constraints or something like that. So we can happily use your no operations as 32. And then I have my overflow here, which was my shellcode. What I'm basically trying to do is getting a shellcode, from my Windows machine, and then we are good to go. And this is your interesting part, which comes here. We get the whole access to the Windows machine. That's really fun. Okay, again, for this step, I might not need my immunity debugger because we're not debugging anything here, just making this kind of big. Okay, and then I run my, remember we put our L port as, what to say, 4444. So I run my listener here. So netcat again is used for listening. So again, this is for specifying the port. This is for specifying verbose, and this is for L, and this is for listener. So L is for listener. This can be in any order, okay? So it can be NVLP or it can be NLVP, anything like that. But then this is for your numeric IP address without any DNS. This is your verbose. This is your L is for your listener and listener mode, and then this is for your port. So I need to give my Windows IP here again. No, sorry, I'm sorry. You don't need to give an IP address. Your thing is you just put your port. Okay. You don't need to give anything. I'm sorry about that. So you just start listening. So you can see that it's listening at any 4444. Now I execute my last and final step, which is your overwrite .py. Things get really interesting here. You can see what's happening here is you're going to give a reverse shell here, and then you're listening to port 4444. That's how we built our shell code. You remember that we put our L port as 4444. So we are going to get something like that. And then if I execute this code, you can see that we got the access for your Windows machine. You can see that I am inside my Windows machine right now from my Kali machine, which is really this one. You can see who am I. You can see that I'm Hari. So literally with a buffer overflow, we literally got the whole access to our Windows machine. And we can do anything here. We can list all the directory here. We can delete his directory. We can also make a persistent, backdoor for his Windows. We could do some command like whenever he opens this Windows machine, always run a reverse shell, without him knowing. So you have these options in your, Windows. So you can always be in his computer. Whenever he switches on his computer, you can always have some access to his computer. So you can always have a backdoor or anything with this. So you got a whole access to his Windows. So what more you want? So you have his whole access of his computer. So this is your buffer overflow. This was the most easiest thing to show because run was the most easiest to show. The thing is, you might have a lot of them. If I again. I'm sorry. Okay, having this one, forgot my. Okay, so what I'm trying to show you is there's a lot of, remember there was a lot of, yeah, it's here. Cool. So you could see a lot of things. The stats was really stable. You had no problems with that. We did run. There are some other stuffs also here. Okay, so if you're wondering what they are different type of buffer which we'll be using. Tran was the most beginner friendly. I mean, you could see everything was, at the starting address itself, we had every, this one. So it was made for beginner friendly. Thing is, you might have your stack, SEH, you might have such a type of buffer overflow attacks as well. You could try doing all these, if you have the knowledge of buffer overflow, you could try doing this, with this same methods. It might be a little bit different because you might get some bad characters. Remember, I was telling about the bad character step. That was the most important step, to be honest. But then, fortunately, unfortunately, you do not have it in your Tran. So you might have bad characters in some other address, which you need to use in your MSF Venom while doing it. You need to be careful over there. And that's it with your buffer overflow. Over to Gautam.
That was pretty good. So I know it might be overwhelming when you first see this, but if you just practice it like once or twice, you'll get to understand what's really happening. The thing is that we just developed the exploit now. So if you want to play it and exploit a machine, you don't have to do all these things again. You just can use the script which we just developed. So if you have any questions, you can ask. That's it from us. If you have any questions, you can ask.